So guys, we're doing this is the second video of refraction of light, and we'll probably do the B and C part of the chapter in this. Both the parts are very small. Okay, first, so in the B part, it's more about the prism. How will the light ray refract through a prism? So last time in the A part, we had learnt about the glass slab, like a rectangular glass slab. How will the light pass through a rectangular glass slab? Out here, we are going to learn about how will the light ray pass through a prism. So first, what is a prism? So I'll just show you a 3D figure of this. So okay, this is how a prism will appear to be. Now, so let's say the front of this is A, B, C. Okay, and the back side of this surface is P, Q, and R. Now the surface on which it is resting. Okay, so this is the one second, R did not come. Yeah, so the surface on which it is resting, that is this surface, is called as what? Base of a prism. So the base of a prism is a surface on which your prism is resting. Then AP. Okay, this side, what you can see, this is called as a refracting edge. Okay, it's called as a refracting edge. We know it's called as an edge, but here we call it as a refracting edge, because this is the line. Okay, this is the line which is formed by the intersection of these two planes. Okay, the plane one here and the other plane is what? From here. And these two planes are called as a refracting surface. Okay, refracting surface, because light will enter from here and exit from the other side. That's why they are called as refracting surfaces. And this angle which is formed out here, the angle on the top between these two refracting surfaces, that angle, okay, that angle is called as angle of prism. Okay, this is called as what? Angle of prism. Angle of prism. Okay, it is called as angle of prism. Now, so they usually do not ask it, but they may ask you to define what is the base of a prism, what are the refracting surfaces, angle of prism, or the refracting edge. Now, but henceforth now, when we are drawing the diagrams, we will not be drawing the whole figure. Okay, we will be only drawing a triangle surface just to show the cross-sectional area. Okay, we'll be only showing the cross-sectional area. So we'll be only drawing a triangle henceforth. This way. We don't need to draw the whole of the 3D figure to show the refraction through a prism. Guys, now once again, I'll draw this prism once again. So say out here we've got a prism. This is the prism. So here okay, so say here we have drawn a prism. Now in this prism, let's say there is an incident light ray first. Okay, what is the incident light ray now? This is an incident light ray. This is an incident light ray. So the light ray which is coming from here, and okay, so this is the incident light ray which is falling normally on the surface, say AB. So this is your surface ABC. Now when the light is falling when the incident ray is falling on the surface AB out here, I'll draw the normal over here. You can draw the normal as a faint line or a dotted line. Dotted line is more preferred. Okay, now this angle which is formed out here is called as what? Angle of incidence. Now when the light ray, when it is traveling from rarer to denser, right? It's going from air to glass. So how will it go? Rarer to denser towards the normal. So now what will you find? That the incident light ray will bend. It will go towards the normal. After this, again, let's draw the the normal once again here also. So Okay, I'll draw the normal here also. Now the normal here is this. Okay, now again when the light ray will travel from denser to rarer, now how will it go? Again away from the normal. Okay, so now this is your refracted ray, this is your emergent ray. This is your refracted ray, this is your refracted ray, and that's your emergent ray. So because it's a refracted ray, I'll write R out here. There is an emergent ray, so I'll write E out here. Now guys, further we'll also mark the angle of refractions. So guys, let's mark the angle now. So we'll mark the angle of refraction. This is called your angle of refraction 1, angle of refraction 2, and this is called as your angle of emergence E. Okay, so I for incidence, E for emergence, and R1 and R2 are the angle of refractions. Also notice right now I have not drawn the refracted ray parallel to the base, so it is not necessary to be parallel to the base. Okay, so this is the path of the light ray through a prism. Now what was the actual path of the light ray through the prism? The light ray should have ideally gone this way, right? I am showing it with the dotted line. This is the path of the incident light. This is how it should have gone. But as we know, it has not gone over there. It has bent twice. Once while entering and once while exiting. Now if you produce the ray backwards, the emergent ray backwards, what will you find? They are forming some angle. And the angle which is formed by them, that angle is called as delta. Okay, not delta exactly, it's called as actually angle of deviation. This angle is called as angle of deviation. Okay, that's the angle of deviation. So what is angle of deviation? Is the angle formed between the incident ray produced forward and the emergent ray produced backwards. Correct? That angle is called as what? Angle of deviation. The angle formed between incident ray produced forward and emergent ray produced backwards. And what do you mean by angle of deviation? Angle of deviation is the angle by which, this was the incident ray, right? Look, this was the path of the incident ray, but it has deviated by so many degrees. So the angle by which it has got deviated, that is called as what? The angle of deviation. What is the angle of deviation? So they can ask you to draw this diagram. They may ask you to define the angle of incidence. They may ask you to label all the angles and all out here. Okay. Now, guys, there is a derivation in the textbook, but you don't have the derivation. So we are not in your portion. So we are not doing it for now. And as you remember, this is called as what? Angle of prism. That's called as the angle of prism. What would be BC called as? Base of a prism. And AB and AC are what? Refracting surfaces. Now, okay, so guys, now first formula that we have in this is that A plus delta is equal to I1 plus I2. So you can write either I1 and I2, or you can write I and E. In the textbook they follow I1 and I2. I think we'll also write I1 and I2 then out here. So this could be either E, or it could be written as what? I2 also, guys. That's the formula. A stands for angle of prism. Delta stands for angle of deviation. Is equal to the two angles of incidence. Okay. Angle of deviation is also given by the formula I1 plus I2 minus the angles of refractions, R1 plus R2. Okay, so yeah, there is one more formula. I'll write that formula later on, because you'll not follow that formula right now. We need to do something else before that. Now guys, we'll discuss the factors. The factors which can affect the angle of incidence. Now, what are the factors that can affect the angle of deviation? Now, to remember these factors affecting the angle of deviation, you can remember this keyword Nike Air. Okay, Nike Air. That will help you in remembering all the three factors. Now, what are the factors that can affect the angle of incidence? So the first factor that can affect the angle angle of deviation is the angle of incidence. Okay, it depends upon the angle of incidence. It depends upon the, okay, so first factor I'll write angle of prism. It depends upon the angle of prism. More the angle of prism, more is angle of deviation. Second, it depends upon what? Angle of incidence. It depends upon the angle of incidence. I'm not writing about it right now. How will it affect directly or inversely? Because it's a little more complicated factor. Then the third one, it depends upon the refractive index of the material. What does it depend upon? Refractive index of the material. That is what? Mu. So these also directly proportional. More the refractive index, more is the angle of deviation. Okay, now in the textbook actually they have given one more point, that is the color or the wavelength of light also. So actually if you realize, the fourth factor is already included in the third one, because the color or the wavelength basically will have what? Different refractive index. Each color, or as the color will change or the wavelength will change, refractive index will also change. So as such, actually the fourth point is already included in the third point, but they have given again here also as a separate point. So saying in terms of wavelength, if you increase the wavelength, what will happen to the angle of deviation? It will decrease, inversely proportional. And for the color, obviously deviation for violet color, angle of deviation for violet is more compared to the red color, because violet travels slower. Now why we wrote air out there? So we wrote air because it is AIR here, see, angle of prism, angle of incidence, and the refractive index. So these are the four factors actually affecting, but I've written only air because the fourth, as I said, is already included in the third one. Now guys, next thing, now how does the, so out of all of them, rest all of them are very simple, right? They all affect directly, inversely, but angle of incidence, it affects in a very weird way. See, how does angle of incidence affect the refractive and the angle of deviation? So see out here, let's say we'll do this graphically. So I'll just plot a x and y axis first. Okay, so let's say now that the x-axis shows us angle of incidence and the y-axis shows us angle of deviation. Now see what happens, that in the beginning, okay, in the beginning, let's say you start your experiment with 0 degree angle of incidence, and then you start increasing the angle of incidence. Now what do you find? As you start increasing the angle of deviation, angle of incidence, angle of deviation starts decreasing. It keeps on decreasing, then it reaches a minimum value, and then it again starts increasing. Got it? So I'll repeat once again. In the beginning, the angle of incidence was increasing. Okay, remember, angle of incidence is increasing throughout. In the whole experiment, we started experiment with 0 degree, then 10, then 20, then 30, then 40, and so on. But what did you find? At some point, your angle of deviation kept on decreasing, and then at some point, it became minimum. And after that, it again started what? Increasing. That's the reason I cannot say it is directly proportional or inversely, because it shows both the type of nature. Okay, so now out here, what is the angle of deviation here? Sorry, so that minimum angle of deviation, what we get out here, okay, this angle, it's called as delta minimum. Okay, what do you mean by this? It is called as what? Delta minimum, meaning the minimum angle of deviation. So until it reaches the minimum angle of deviation, the value will keep on decreasing, and then after that it will start increasing. So delta minimum, and this is what? The angle of incidence at that point. Okay, so this is how you have to plot the graph. It's very, very important graph, and all those who are Nike fans, they will know it, why I call this graph as a Nike. You can look at that curve, just do it. Okay, now guys, next thing, now there is one special case under this. So what is a special case now? There is something which is called as a delta minimum, right? We already discussed what is delta minimum, the minimum angle of deviation which can be obtained in a prism. Now whenever you will reach this angle, at that time your refracted ray will become parallel to the base. say, as I told you earlier, it is not necessary a refracted ray have to be parallel. Only under this one condition it becomes parallel. It will be what? Parallel to the base. Okay, it will be parallel to the base. Second thing, your angle of incidence becomes equal to the angle of emergence. Third thing, your angle of refraction 1 is equal to angle of refraction 2. In fact, that's the reason, because R1 is equal to R2, then I1 becomes equal to I2. Okay, and the one last thing was what? Delta minimum, meaning all these four things now, all these four things that I've written, they all will happen at the same time. Okay, they'll only happen at the same time, that R1 equal to R2. Okay, now also guys, one more thing, when this is happening, okay, look at this, when there is a delta minimum, so look, how will your figure be, how will your diagram be at that time? So what will you find is that say if this was your incident ray, say this was your incident ray, okay, look, let's say this is your incident ray, then your refracted ray over here will become what? Parallel to the base, and then again it will go there. Got it? So it will be parallel only under this condition. What is the condition? When delta is minimum, not otherwise. Now see, just for your understanding, I'll give you some numbers just to make you understand all this better. Just one more thing, if I1 is equal to I2, what can you say that time? Angle of, what can you say about the delta? It is minimum. So see, now I'm adding up here one more formula. What's that formula number 3 now? That if, okay, what is the formula number 3? That angle of prism plus angle of deviation, if it is minimum, then instead of I1 and I2, I can say, right, I and I only, because they are equal, correct? So your formula becomes what? A plus delta minimum is equal to what? 2I. That's your total, right? So this is a new formula, formula number 3, that A plus delta minimum is equal to 2I, meaning twice the angle of incidence. Okay, and yeah, so that is all. Okay, just one more thing I wanted to tell you. Look at this now. We'll just take some values and I'll explain you. Let's say for an example, for a value of 48 degree, say angle of incidence was 48 degree here, and the angle of deviation you got here was say 36 degree. That's the minimum angle of deviation. Now my question is that if the angle of incidence is increased to 60 degree, what can you say about the angle of deviation? How much will it be? Will it be more than 36 or less than 36? Okay, you thought of the answer? Okay, I'll tell you. The answer will be what? Your angle of deviation will be more than 36 degree. You can look at this graph here now. How? It will be more than 36 degree, correct? Because it is going above that. But what if your angle of incidence is lesser than 40 degrees? Say your angle of incidence is only 30 degree. Then what happens to the angle of deviation? Will it be still more than 36 degree? Yes. Okay. This might sound very stupid now, but then there are too many students who fall for it. They do not realize it has to be more than 36 degree. Again, more than 36 degree. Basically, at any other angle of incidence other than 48 degree, what can you say about angle of deviation? It will be more than 36 degree. Because the minimum value is only 36 degrees. So it has to be what? Greater than 36. Okay. So this is all you have in the B part of the chapter. So as I told you, it's very small and very simple. Guys, we'll begin with the C part now. Even C part is quite simple actually. But there are a lot of drawings, guys. So you have to be good at drawings in this one. Guys, you'll have to manage the drawings on your own. Draw properly. I'm not there to check your drawings. Because as I told you, this chapter is just more about drawings. And they always ask drawings from this chapter. So draw all the diagrams only with a ruler and pencil. Do not believe in freehand. Don't draw with a pen directly or freehand or something. Okay, it will help you in the boards, believe me. So guys, now we are doing the C part. In the C part, we are basically mainly learning about what, these are the two terms we are learning about: real depth and apparent depth is what we are going to learn about. Real depth and apparent depth. Now, okay, so let's start. Now, what do you mean by real and apparent depth? So first, like you must have noticed, like when you are, if you're standing, uh, if you're standing closer to a pool, you must have seen that pool appears to be shallow, but only once you jump into it, then you realize that it is deeper than you thought of. Or like when you stand in a swimming pool, you find your legs to be short, or short people find their legs very short in a swimming pool because of the refraction of light. Okay, that's all. This is got because of what real and apparent depth. You can try these at home. Take a glass, okay, transparent glass, fill it with water, and keep it on a newspaper or on a print. And when you look from the top, that print will appear to you a little raised. Or you can also try dropping a coin inside it, and again look from the top. That coin will appear to be what bit raised. So because of that, it leads to what real and apparent depth. That is because of refraction of light. So we are just going to discuss about what is real and apparent depth, and there are 2-3 numericals you have in this, and there are other couple of give reasons and diagrams. Okay, so guys, see, let's say first we have placed. I'll give you an example. Say this is your surface first. So okay, that's the surface. Here we've got water, and say here it is air. So how is the light ray going from denser to rarer medium? Now let's say over here we have taken one point here inside. Now how will the light ray go from this point? So it is going from denser to rarer. So it is supposed to go how? Away from the, it's going from denser to rarer. Doctor ran away. So it is supposed to go how? Away from the normal. So your light ray will go, say this is how it will go. Okay, one second, I'll draw it again. Okay, it will, let's start from this point. So it will go denser to rarer. So it's going to go how? Away from the normal. So this is the one ray. We'll stop here. Then again it is going from denser to rarer. So how is it going to go? Away from the normal. Now guys, what we'll do here is I'll also draw the, so first see, let's say your object was placed here. Light ray started from there. It's going from denser to rarer. So how will it go? Away from the normal. And this is your normal. Okay, this light ray is your normal. So once again, this is I'll just mark all the things now. This is the incident ray. That's your normal. This is your refracted ray. Now if you are viewing from the refracted ray, if you are looking from this side, let's say you're looking from here. So when you're looking from here at the light ray, what will you feel? So this is eye, guys. If you can't make out, I'll write for you here. This is an eye. So when you're looking from here, you do not come to know that the light ray must have bent while coming out from water to air. You do not realize that. Your eye will not be able to make out that. So what will happen? You will feel as if that the light rays have come from this point here. So the point which is actually below over here, that point A, it appears to be where? Here, A dash. Okay, so this point will appear to be what? Raised to you, and that's called as what? Apparent depth. Apparent depth means what? The false depth, what it appears to be. It's not the actual depth. And you must have noticed that apparent depth is less than the real depth. So this is called as a real depth, meaning the actual depth, and this is the apparent depth. Okay, so these are the two depths we will be discussing in this chapter. Okay, so first thing to note over here, that the light ray is traveling from denser to rarer, and then the real depth was coming more than the apparent depth. Okay, so as I gave you an example, the pool will appear to be what? Shallow. So there are many such examples that's given in your textbook, and like they have given, and on page number 90 in your textbook, they have given some 7-8 consequences of what can happen due to refraction of light. So more or less all of them will have the same kind of a give reason. What is a give reason? If they ask you for all of them, I've marked on page number 90 in your textbook. Okay, page 90, left column, first paragraph. You'll find over there, see they have written, this is due to refraction of light from water to air. The rays of light, when they are coming from water to air, they will go what? Away from the normal. But when you're viewing from outside, you will feel that these light rays are coming from a point above it. And that's why it will appear to be what? Raised. Is it clear? So if they ask you to show the real and apparent depth, you may draw this diagram. You can just draw one more ray out here. Remember one more very important thing, that this point A dash are always in the same vertical line. Okay, it is in the same vertical line. You can draw that line dark also. I just dotted it to show you for now. Okay. Now, let's say if this point was your object, say point O, then what is the real depth? OA. What's the apparent depth? OA dash. Okay. Now one more very important thing here now, that this distance, what about the distance between them? A dash. So this distance is called as what? Shift. SHIFT. I'll just write it out here also again. That here your shift will be equal to real depth minus apparent depth. The difference between them basically. So by how much it appears raised, that is called as what? The shift. Okay. So this is one of the formula you're going to use, and the second formula is a refractive index. So what's the formula for refractive index now? One more over here. It's a ratio of real depth upon the apparent depth. Okay. So as I said, we do not have this formula, the derivation. We'll see later on when we have time. If you have time, we'll do it later on. For now, to keep it short, I'm telling you only the formula. Okay, there is one more formula in your textbook, though I don't use this formula actually, because you can do all the problems without using this formula. The other formula is that shift is equal to, you can use this also, it's also convenient to use actually sometimes, is equal to real depth into 1 minus 1 upon the refractive index. But refractive index should be what? Of the medium with respect to air. So that is the shift. Okay. Like for example, here we will take refractive index for water in the example that I've discussed out here. Now guys, next thing is the factors. What are the factors which can affect the what are the factors which can affect the real and the apparent depth? So, or rather, let's say what are the factors which will affect the shift? By how much is the point appears to be raised? So there are 3 factors in this one. And to learn these 3 factors, you can just remember RTC, reference to context. What does RTC here mean now? Okay, if you can make out, the first point is what? Obviously what? Refractive index. So it will depend upon the refractive index. How does it depend? Directly proportional. More the refractive index, more the shift will be. Okay, second point is the T. T means what? Thickness. How will the thickness affect now? More the thickness, more will be the shift, because then more thickness means what basically? For example, if a pool is 4 meter deep and if a pool is 10 meter deep, so 10 meter deep will appear, there will be more shift in that. Okay, meaning the lower post, the ground will appear to be more raised in that. Obviously, why? Because the thickness is more. And the point number 3 is the color or the wavelength of the light. So that's color or wavelength of the light. It depends upon color or wavelength. C for color and wavelength, lambda. Now how will the color or the wavelength affect? So can you try which color will have the maximum shift? Violet color. Violet color will have the maximum shift. Why? Because it travels the slowest or maximum refractive index. And wavelength, so we can say what? Wavelength and shift are inversely proportional. So lambda is inversely proportional to shift. More wavelength means lesser shift. So red color will deviate less as compared to the, or red color will get shift less as compared to the violet color. Okay guys, so these are the factors, 3 factors which can affect the refractive index. Affect the shift. Let's see, one more thing, very quite logical, will make you understand better, is that when I tell you the refractive index of glass is equal to what? 3 upon 2. And what's the formula for refractive index in terms of real and apparent depth? It will be real depth upon apparent depth. So what does it mean? The ratio of your real depth is to apparent depth will always be equal to what? 3:2. Like for example, let your real depth be equal to say 30 centimeter. What will be your apparent depth is equal to 20 centimeter, because then the ratio 3:2. And what is the shift produced out here? It will be the difference, 10 centimeter. That's the shift. Okay, so that is how this will help you. So sometimes they usually do not ask you, sometimes they may ask you to draw a diagram of real and apparent depth with respect to this particular ratio also. Okay, they may ask you to draw it with this particular ratio. They are not asked so far, but just they may ask you that to show the real and apparent depth for glass or something, and they might give you some thickness. Okay, next thing now. Okay, there is one more application, guys. Now this is also nice application. Say you have we've got a glass slab out here. Let's say we've got a glass slab here. Now what is so special about this glass slab is that they have printed the alphabets Vibgyor. Okay, they have printed Vibgyor at the bottom of this glass slab. And every color, okay, I have written everything in black, but actually every color is given in what? Is written in their respective color. Like V is written in violet, I in indigo, B in blue, so on, and R in red. Now when you're looking from the top, when you're observing from here, from the top, okay, my first question is, will all these alphabets appear to be in the same plane? Is the first question. So first thing, will they all appear to be raised? Will they all appear to be in the same plane? No, they all will be raised. Next question, will they all appear to be raised or no? So first thing, they all will be appear to the raised, that's true. But will they all be appearing to be raised to the same level or no? That's a question now. So they will all not be appearing raised to the same level, remember. What will you notice? That violet would have been raised the most. Then indigo, then blue, then green, yellow, orange, and then red color. Okay, now the question is why they are all not raised to the same level? Because they all have got a different refractive index. So as you can see, who's got the maximum shift? Okay, if you notice properly, violet has got the maximum shift. It is raised the most, so it has got the maximum shift. Okay, but in the exam they will try to trick you. They'll tell you who's got the maximum apparent depth. Still people write violet only. Who's got the maximum apparent depth is this. Depth is measured from the top, remember. So this one has got maximum apparent depth. Fine. So maximum shift, and this one has got a maximum apparent depth. Okay, that's how you get this. These have come for 3 or 4 marks. So they may ask you first, do they all appear in the same plane? You say no. Which color appears to be raised the most? Violet. Who's got maximum shift? Violet. Okay, and who's got the maximum apparent depth? Red. And why? So you can blame it on whom? Refractive index. Remember, in most of the places everywhere we always blame it on the refractive index only. Okay, now another thing which is very interesting, guys. Okay, first I'll show you one more diagram. So this diagram is to show the bending of stick. Okay, I'll try to draw it out here. I may not be able to draw properly. It's difficult to draw it over here. Okay, on this tablet. Let's see, we'll try. But otherwise you all can refer to the figure 4.37 in the textbook. Refer to the figure 4.37. Guys, this is one of the most important drawing. Okay, I have by mistake marked it 2 star. You will make it 3 star in your textbook. It's that important. So let's begin. We'll try. So first we'll draw out the interface. So this is the interface. This is the interface between the water and air here. Okay. So we've got what over here? Water. Out here what is there? Air. Now here we are going to draw a stick now. So we are drawing a stick which is partially submerged. Okay, I'll repeat again. It is just what? Partially submerged. It is not completely submerged. So some portion of the stick is what? Inside the water. Now guys, how to draw it further? So now see what you need to do. We will mark another point P dash. Let's say this is your point what? P. And that point on the top is what? X. So this is PX. Now before and only now we are going to mark another point P which will be above, sorry, P dash, which will be above P. So I have marked the point P here above it. Okay, now we have to draw. Now let's start the diagram now. Now I'll tell you the logic. What is the logic of drawing this diagram? So what we are going to do here, we are going to take two light rays which are starting from this point. Okay, first what we are going to do, we are taking two light rays which start from the point P. So they are going from, let's say they go from P to here, right? One light ray, and the second light ray starting from here to there. Okay, now guys, second thing which is little difficult to draw. So these are the two incident rays we've drawn. Obviously they'll go what? Away from here. Now see, they will go where? Away here, and this will also go away because denser to rarer is what? Away from the normal. So these are our incident rays, these are our refracted rays. Now what the problem is, when you produce this light ray, see again we are looking from here. So this is your eye again here. Those who don't believe, I'll write for them eye. When you draw these light rays backwards here, okay, draw these also backwards here, what should happen? They'll supposed to, like when you produce them backwards, they're supposed to come from this point, correct? But you must have noticed now that this line which I have drawn, you can see it is not going a straight line. It is supposed to be straight line because I'm producing it backwards. But you can see the light ray is bending here. The light ray here also is not straight, it is bending. So we have to do something so that you are able to draw a straight line. How to obtain that? I'll show you that now. So guys, see, we'll have to do a little bit of manipulation here to draw this diagram now. Okay, so I'll just remove all these lines first which I drawn earlier, which I don't need actually here now. I don't need this line and this line. Okay, so now guys, back to this. We are going to do what, we have to draw we'll start drawing from the point P itself. Okay, so say what you do, you keep your ruler on the point P dash here down. So this is your P dash and you should keep the ruler at the point P dash. Start from the point P dash. Okay, go to that point which is on the top there. Okay, where the refracted ray, the first incident ray is meeting the interface, and start from there. So you'll have to draw this line dotted and then straight out. Same way you have to draw the other light ray also. Again start from the same point P dash. Try to draw dotted line till there, and when you're moving out it should go what? Straight. And then again it will be what? Straight out. So these are your refracted ray, and when you produce them backwards, what has happened? It is meeting back at the point P dash. Guys, we would have finished this diagram only because of this drawing. It took some time. Now what will happen to this stick now? The stick which was earlier straight, now it will appear to be coming from this one point out here. Okay, and that point is what? P dash. Is it clear? So a stick which is inside the water, it will appear to be bent and raised. And who's to be blamed for this? Refraction of light, remember. Okay, guys, now one more and the last diagram that we need to do here is so far we have considered when the light rays are coming from the water to air, meaning we are in the rarer medium. But what if we were in the denser medium and looking at an object which is in the rarer medium? Then see guys what will happen. So say here, this is again the interface. We've got here water, and here what you have, air. So this is a rarer medium and this is a denser medium. Now let's see what happens here. So first what we'll do, let's say there is a tree out here. Okay, so I'm saying that, say there is a bird who's sitting on a tree, and there is a, or I'll not draw this right now. Let's say there is a fish inside the water here, and the fish is looking at the bird who's sitting on the tree. So the light rays will start from here, right? Okay, let's say the light ray will start from here, from denser, it'll reach till here. Okay, now what we'll have to do, first you can draw the normal here also. Now the light ray, when it goes from water to air, how will it go? Away from the normal, right? This is how the light rays are supposed to go. But one second, I think I'll start the diagram other way. Let's say we have got a bird sitting over here. Because I'm drawing the bird on the right hand side, though in your textbook they have given the bird on the left side and you're observing. I'm drawing the lateral inversion of that. So the light rays are coming from here and they are going towards the fish. So it's rarer to denser, so it will be towards the normal. Okay, you assume it was a straight line. So this is how the light rays. So but when the fish will actually look outwards here, okay, this is how the light rays came, but when fish will look out from here, what will happen? What will fish feel? That the light rays must have actually come from a point which is vertically above it here. So this is your actual depth, right? But what will be your apparent depth? This, it will appear to be what? Bigger. So say if I mark this as your point O, this will be what your O dash, and this is what your A. Now here if you see, your real depth is what? AO. What's your apparent depth? AO dash. And you can see your apparent depth is what? Greater than the real depth. When will all this happen? Only when the light ray is traveling from where? When you're observing from where? From denser to rarer. Earlier it was how? Rarer to denser, but now you're observing what? Denser to rarer. Got it? So yeah, this is how it will appear. Yeah, as I told you, my lines are looking more like a curve or throughout a bent line, but you need to draw it properly. So you can refer to the textbook diagram to be more accurate. Okay. Then guys, now next thing, we'll do the numericals here now. Even the numericals are quite simple here. I'll show you all the three numericals. So first numerical is 1 star. Now see, it's given that a water pond appears to be 2.7 meter deep. Underline the word appears to be. So that obviously means what? Apparent depth is how much? 2.7 meter. If the refractive index of water mu is equal to 4/3, find the actual depth of the pond, meaning find the real depth. Underline actual depth also. Guys, I'm not doing this problem. You'll try it on your own. That refractive index is equal to real upon apparent and solve it. So you'll do it on your own, guys. Problem number 2 is a 2 star. A coin is placed at the bottom of a beaker containing water whose refractive index is 4/3 at a depth of 12 centimeter. So real depth is equal to 12 centimeter. By what height the coin appears to be raised? So underline the word raised. Raised basically means what? What will be the shift? So what will you do in this sum? First you will find out what? Apparent depth, using the same formula what you'll use in the first formula, but that's not your answer. When you will solve, your apparent depth will come what? 9 centimeter. Correct? Your apparent depth will come 9 centimeter. But what are you asked to find? The shift. How will you find that shift? 12 minus 9. So that is what? 3 centimeter. Okay. Next question, guys. Number 3. Third one. Now, a postage stamp is kept below a rectangular glass slab of refractive index 1.5. I'll write it in fraction 3 upon 2. When viewed vertically above it, guys, underline the word vertically above. So this had led to too much of controversy when it came in the exam. See, when they say vertically above, the question is whether is it perpendicularly, whether you're looking normally from above or perpendicular, because then there will be no refraction in that case. Okay, anyways, guys, see, we'll assume that there is a refraction, guys, so I'll avoid all this confusion over here. Okay, now let's say they have given what, that we've got a glass slab here. Now guys, in this glass slab that they have given, what is given to us also is that they have placed a stamp at the bottom, and that stamp what they have marked at the bottom, it appears to be what, raised, meaning this stamp appears to be raised, it appears to be here, and it appears to be raised by how much, 7 mm, that is 7 millimeter. Okay, if it appears to be what, 7 millimeter. Now they are asking us to find the thickness of the glass slab. What do you mean by thickness? Thickness would mean what, the total real depth basically. What is your apparent depth, guys? Now find out that first. What will be your apparent depth? It will be x minus 7. That's the only catch. Your apparent depth is not 7, it is x minus 7 because it is measured from the top. So that's your real depth, that's your apparent depth, and then use the refractive index formula. Mu is equal to what? Real depth upon apparent depth, and then done. Okay, guys, for homework we should do circled questions and numericals of 4B and 4C. Okay, so all the circled questions of 4B and 4C is what we need to do for homework. Okay, done.